Good morning, everybody. The senior author of this paper is Chuan-Yu Sun, and he's not here. Well, he's not in maternity leave, but so it's not here. So he asked me to present the paper, and we felt that could be interesting to you because it provides a proof of concept. And even if it's not black and white, you may consider Angus as an approximation to black and white, fairly black. So let's see. What do I have to press here to go down? Okay, here. I think everybody knows that there is a great deal of interest in imputing moderate density, 50K today is a moderate density chip from low density chip, primarily to reduce genotyping cost and also arguably to improve the reliability of genome-enabled selection relative to what you will be obtained by using a low density chip without any imputation whatsoever. I'm not a specialist and I don't know the details of these, but essentially there are two types of imputation methods, ones that are family-based and the other ones are based on population-based algorithms. The first ones use linkage and Mendelian segregation rules, and the second ones essentially exploit linkage disequilibrium between a given SNP and observed flanking SNPs. Many such software imputation packages are available. Some are listed here. We concentrated on the top 6: Beagle, Impute, FastFace, Alpha Impute, FineHap, and F-Impute. The rest, the ones in the bottom are just shown to illustrate that those are not the only available imputation packages. And those of you, I haven't had any experience, they probably have observed that there are inconsistencies among programs, and a challenge is how to solve such inconsistencies. Now, we here will be focusing on on this problem as a classification problem, and in machine learning context, you will regard each of these imputation softwares as a single imputation machine, providing in some sense an independent classification. Whereas in machine learning, like in most areas of predictive science, it is known not only from theory but from practice that most of the times, on average, the best predictions are obtained from some sort of averaging. One good example is Bayesian model averaging. So the idea here is to use an ensemble, a collection of imputing machines that will combine the outputs from each of the multiple models, combine them into a single imputation, and these arguably would provide a more reliable result relative to those that you would expect from the use of a single imputation software. And one of the most widely known classification algorithms that exploits ensemble learning is called AdaBoost and has been floating around since the early ideas were in the 90s, and the proofs of why AdaBoost works have been published in serious journals, such as the Annals of Statistics. So here we had a dual objective. One was to investigate the performance of an ensemble approach when we were imputing high-density genotypes. As I said, actually this is moderate density for today's standards. And then we addressed the issue with a sample of Angus cattle to see what will happen if we impute from a low-density panel to the 50K chip and see how the ensemble would behave. So essentially, we had a sample of bulls from the Angus breed. They were all sires, and they were all pedigree with a large enough depth. These, after filtering, had 49,083 SNPs. And then we constructed a training set partition, actually, that had 2 folds with about 2,300 animals and a testing set of 777 animals. And what we did is we bootstrapped the testing set 50 times to obtain an estimate of the conditional cross-validation error distribution. There are different cross-validation errors. An unconditional one is when both the training and the testing sets vary at random. Here we fixed the training set and we bootstrapped the testing set to approximate what would you expect if the testing set were repeatedly sampled from a given population. And of course, bootstrapping is a sampling method with replacement. And imputation was done on a chromosome by chromosome basis. Here we will be focusing on 3 chromosomes, 1 the longest, 16 medium size, and 28, which is one of the shortest. And as I pointed out earlier, the 6 imputation softwares are listed here, and we use an AdaBoost type algorithm. So I will briefly try to describe to you how AdaBoost works. We have T classifiers, in this case 6 imputation softwares, and then at any point in time, you are on a given classifier, call it T, you compute the error rate. And this W is a weight that originally is the same for every observation, and the I is an indicator function. Namely, if the indicator function is 1, you have made an error. So essentially, E epsilon T is an error rate. So then you compute some sort of a tuning parameter called beta T, which is the logit of the accuracy divided by the error rate, and if the odds are larger than 1, then beta T is positive. If the odds are smaller than 1, then beta T is negative. And then you proceed to the next classifier. Let's say we are in 1, you move to 2 by updating the weights. And the way that this works is that you put more weights on observations that were incorrectly classified by the first classifier. So in that sense, by going through all the classifiers in the ensemble, you concentrate more and more on the errors that have been made by the preceding classifiers, hopefully trying to correct them all. So at the end, there is a voting procedure in which you use the final results from all the T classifiers, and you weight them appropriately, and you come with a vote. And the assignment to a particular genotype is the one that receives the largest number of votes. That's called a voting committee in the machine learning jargon. So this is a hypothetical example just to show you how it works. Here we simulated 800 animals, and we tried to impute a single locus with 3 genotypes. In the table below, you have 8 classifiers that differ in their accuracies. For example, 1 has a 0.5625 accuracy, and 8 has a 0.975 accuracy. So 1 is considered a weak learner, and 8 is a strong learner. And then you see that if you are working with weak classifiers, if you use 5 and you use the AdaBoost algorithm, you improve the classification accuracy to about 33%. But if you use 100, you get a perfect accuracy. And of course, if you start with a strong classifier, the room for improvement is much lower, but you still should be able to come up with a perfect imputation, in theory. So now I'm going to show you some results from the 6 individual packages for the 3 chromosomes. For instance, in chromosome 1, Beagle had the best performance with a median 0.99% accuracy, whereas F-impute came as number 2, and alpha impute was the 6th with about 0.91 accuracy. And this more or less was observed in each of the chromosomes. So there was a bit of variation among packages in imputation accuracy, sometimes of the order of 10%. So here we had 6 packages, so we could construct, in principle, 720 combinations, each defining a unique ensemble system. For example, you could start with Beagle, then follow with alpha impute, then followed by F impute, and if you permute all these, you have 720 possibilities. And we actually did them all, and we bootstrap each of the results 50 times. So we had 36,000 jobs, which you have to multiply times the number of chromosomes. So it was a formidable computational thing. So we use distributed computing via accessing the University of Wisconsin conduct systems, where at any point in time we had to our availability to over 2,000 servers. But one of the requirements is that your job has to be finished within a day, otherwise Condor will kill him. But in this case, each job didn't take too long, so we were able to successfully complete this computation in a reasonable amount of time. This is the conditional bootstrap distribution of the prediction errors from left to right in this box plot. We have the first 6 numbers are the individual imputation machines. Number 1 is Beagle, And then 7, 8, 9, 10, and 11 are 5 ensemble systems. And here you don't see big differences because Beagle, to begin with, is a very strong learner with an accuracy close to almost being perfect, but we did slightly better, as I show later on. This is chromosome 16, this is chromosome 28. So the results were consistent across chromosomes. So the result from this first exercise is that the ensemble method was better than any of these packages, of course, very little with respect to Beagle, but very much better than with alpha impute that typically came to be as the lowest ones. We did find that the sequence of packages in the voting process affects imputation accuracy, and the best accuracies were typically the sequences that use Beagle as a first machine, followed by some of the packages such as alpha impute that use pedigree information. So now we'll proceed to the Angus application. As I said, we had low density panels of 7K, and the objective was to impute a medium density genotype of 50K, and we did that for all of the 20 same chromosomes. And we did it for the 6 packages and for these 6 collection of ensemble machines. You can see the order. Always started with Beagle and then followed by alpha impute in the second order. And these are the results. I'm not going to show the bootstrap distribution because it's a very involved sort of graph. But in the top, you have the 5 top ensemble systems. There were some that were worse, but you'd expect that on average this will be better, and that's what we found. Then we had Beagle. Then we had the one with the circles, which F impute, and as you can see, each of the 29 chromosomes considered alpha impute had the weakest performance. So individually, in this example, Beagle and F impute are the most accurate. We were able to verify what we expect from theory, that the ensemble method do solve inconsistencies, and sometimes they lead to an increase in accuracy, especially when the individual classifiers are weak. We found that the order of classification of the classifiers matters, and that when constructing ensemble systems, at least in this particular case, it was found that those that start with Beagle and then use some imputation machine based on pedigree have the best performance among the ensembles. So on that note, I wish to thank you very much for your attention. If there are any questions, I'll try to field them. Thank you.